Okay, so we're trying to find the force on an arbitrary charge of big Q. So we're going to regard this as a test charge due to a charge delta Q out here at a point whose polar coordinates are r theta. So how do we do this? Well, Coulomb's law applies. It's written the way we write it in terms of an r vector, which isn't necessarily the polar coordinate, okay? So r is the length of this vector. That's the polar coordinate. It's not a vector itself. And actually, I maybe could have been less misleading if I just not put an arrow on that. But the r vector that we're going to use for Coulomb's law goes from this point to the point where we're calculating the force or the field. Okay. Remember how I stated it. The r vector goes from Q1 to Q2, and that gives you the force exerted by Q1 on Q2. So we're going to start with the force exerted by the delta Q charge here on charge big Q. So the r vector has to go from here to here. Okay. Now, from that, the force big Q delta Q K times the product of the charge over the square of the r vector. That's a vector force. We're going to have the vector times the r vector over r. Now this is the r vector. Its magnitude is r because its length is the same as the polar coordinate of this point, since Q is at the origin. Okay. So that's a simple way of writing it out. There's the force. So the electric field is the force per unit charge. So it's K times delta Q over r squared times the r vector divided by its magnitude. Well, but that's just magnitude of the r vector is just r. And we could summarize that as K delta Q over r cubed times the r vector. Make sense? Okay, well, now if we're going to do a vector, it's simpler to do a vector in rectangular coordinates. Notation's simpler, and you're not carrying a coordinate system around with your point, and it's just a whole lot easier. So we're going to do this in terms of the components of R. Now, the only thing that needs components of R is here. Now, one thing I'll say, when we combine this R with this R squared, we only have one term for the distance R. Okay, whereas really when we think through this, one of the R's is what we have to use to get a unit vector out of our R vector. The other is the inverse square. So this almost makes it look like there's an inverse cubed law. You have to keep in mind that this R isn't a unit vector until you divide it by one of these R's here, okay? So the advantage is keeping it in this form because it reminds you why you're doing it. In this form, it's a little less obvious. Similar to what I've said in multivariable calculus about the projection. There's a formula for projection that disguises the meaning of the process. And I really don't like that formula because people never really understand it. If they just use the formula, or very seldom really understand it. Okay. Anyhow, There we have it. So this equals what? Well, R is in the direction opposite a vector from here to here, which would be at angle theta. So this is actually an angle theta plus pi, or theta plus 180 degrees. So we could say this is R cosine and this is R sine both of theta plus 180 degrees. You look at the direction of R. Direction of R with the pole is theta plus 180 degrees, and that's the negative, okay? It's just the vector directly opposite. So all kinds of ways you can write that down, so you want to be aware of. Okay, well, we're going to use this. And now calculate here's a semicircle. And it's got a charge density lambda. Okay. So we're going to say that delta Q equals lambda delta S, where delta S is the length of this interval. Okay. Now that could be a delta theta interval, and we could then see that the length of the intervals are delta theta, and we could do it that way. Okay. Plenty of ways to do this. So I'm just going to say it's a delta Q equals lambda delta S. Okay. So for delta S, I don't have a good place to label it. There's delta S. We've got to charge delta Q here. I'm going to draw an arrow. So the only thing that would be different in our expression would be instead of delta Q, we'd have lambda delta S, right? There's another thing we can do in our expression. We can divide one of these R's into the R that we factor out of this expression. And now it looks like an inverse split. But what I do is I'm going to set up another equal increment out here. Same angle theta, same delta S. Now, can we draw the vectors? Got the picture and you have room. If not, you can resketch it real easily. You have the picture. What's the vector force here? What's the vector field here? What's the direction of the vector acting on this? Well, it's going to be there. Now, instead of F and E, I'm going to call this delta F and call this delta E, because these are now contributions to the net force on this test charge due to all the charge on this semicircle. That make sense? So we started with just the delta Q up here. And we got our expression for that. And then we said that delta Q was a lambda delta S, where delta S is a distance increment along this arc. Got a question? Okay, now somebody just asked a question that anticipated where I'm leading. There's a symmetry argument that says all you gotta do is find the x's. Okay? Well, that's why I was asking you to draw the vectors, okay? So we've got this vector. Let's call this one delta E. And the notation's going to be a little funny here, but the other one would have another delta E here. So we could call this delta QI. And okay, the notation's being a little. Rho is delta Q. And I'm going to call this delta Q prime. So I'll have a field here, delta E prime. Okay, well, can you write out the expression that we would get for delta E prime? Now you go through all the details. You can say the theta, that this theta, actually they're measured from here and so forth, would be this, that, and the other thing. But what's obvious is the symmetry of the situation. So that this vector makes the same angle with the x-axis as this vector. So that its y component is equal and opposite to the y component of this one. Now, if you write out your delta E prime, let's write it out. Okay, it's going to be same as this, except the sine of theta will be plus sine theta times j. Okay. Now you can write out all the details. You can write out what this vector is in terms of this vector, and you should be able to do that. But in physics, a lot of times we'll kind of gloss that over. It's pretty obvious from the picture that these angles are equal and the magnitudes are equal, since delta Q prime has the same magnitude as delta Q. So that delta E plus your delta E prime just equals negative 2k lambda delta S over R squared times cosine theta I. Now that's pretty small, but we're getting a negative cosine theta I here and a negative cosine theta I here, both multiplied by the same factor, and we have this. Does that pretty much make sense? Pretty obvious that this is a semicircle. These increments are at equal distance from the origin. So the magnitude of the electric field due to that increment is going to be the same here as it is here. The symmetry that I've imposed here by putting theta here and another theta here, that tells us that the y components are equal and opposite. So when we add the two electric fields at this point at the origin, we're going to get zero. And we're going to get zero y component. We're going to get a double x component. So what we have is here it is. What we have is we have this component and this component of this field, and this component and this component of this field. I would have drawn this head to tail, but my label was in the way. So this component and this component are equal. So we're going to get double either one of them. This component and this component are in opposite directions, so we get zero. So just get an x component. Okay. Now let's set this up. What? Here we have our x and y axes. Here we have a test charge, capital Q. Here we have our semi-circle. Radius R. Times the charge density lambda. There are a number of ways we could parameterize this semicircle. The way I'm going to choose to parameterize it is theta going from negative pi over 2 to pi over 2. Divided up into intervals of length of r length delta theta. Theta from negative pi over 2 to pi over 2. So we get negative pi over 2 equals theta naught. we partition a theta interval from negative pi over 2 to pi over 2 in equal increments of delta theta. Now, so we're going to use equal delta theta increments, although equal isn't absolutely necessary. As long as the mesh of our partition approaches 0, we're still going to get a good interval. Typical increment. Here we have delta theta. Here we have theta I minus 1. And here we have theta sub I. So that would be like here's our typical increment. Okay. We have a delta S here. And what is delta S in terms of the symbols we have on the board? Okay, so we got several partial responses to that until by just asking a couple of leading questions, pretty quickly got to delta S is R delta theta. That's by the definition of radians. Okay, delta S is the arc distance. First answer I got was, well, it's the arc distance. Well, what arc distance? What's your expression for the arc distance? So it's, well, delta theta. No, delta theta is an angle. And then I immediately got, oh, R delta theta. Okay, so that needs to be just something that stays obvious from now on. Okay, so delta S is R delta theta. And then no matter where I label this thing's going to be on the way because I'm not good at anticipating. Okay, I'm going to label my theta I here. It's just this angle down here. And now I can draw my electric field. And this will be now delta E sub I. We've seen in terms of this picture, I think we can still see that for any delta S on this side, we can have an equal delta S on the other side. Okay. Now I could have specified, okay, we partition this in such a way that we have a whole number of increments from here to here and a whole number of increments from here to here so that we can match them up, one here with one here. Okay. That makes sense? And if we can match them up, one up here at an equal angle from the pole or the x-axis, and one down here at the same angle, but on the other side of the axis, we know that the y components are going to be equal and opposite, so they're going to add up to 0. Okay. So from that symmetry argument that we already made in one of the class identified, we have the x component of delta E sub I. And that delta x, or that x component, if we just look at what we did, I'll reason it out again because it's fairly straightforward reasoning. Equals lambda R delta theta over R squared times cosine theta sub I times the I vector. I think I've got everything there. Yeah. Because here's the amount of charge we have in this R delta theta increment of the arc distance of the arc. Okay, so we multiply that by the charge density. This gives us our charge. We began by postulating a test charge at this point, but we know that if we want to get the electric field, we divide the force by the test charge. So we have a force, we divide the force by test charge. We talked about that last time. We have this, okay? So that the total field at the origin, let's see if I'm still on the board. No. And the field at the origin is approximate. Sum from I equals 1 to n. Delta E sub I x component, which is the sum from I equals 1 to n. And I'll put my A lambda R over R squared out here in front. And of course, the R divides the R squared. We'll do that in a minute. And then we have the sum of what? Cosine theta sub I. Now, when I wrote down cosine theta sub I was a little careless. That should be a cosine of theta sub I star, a sample point, a sample angle between theta sub I minus 1 and theta sub I. So let me insert that. Theta sub I star is something, some angle between this one and this one. Okay, so that should be a total theta sub I star. That can be important. And I'll even factor my I vector out because it's common to every term. Well, this approaches lambda over R times the integral from negative pi over 2 to pi over 2 of cosine theta d theta, and I left off my delta theta here. And that should be familiar for first year calculus. It isn't, you know, you really need to make sense of it. It's how we set up intervals, okay? Don't do it by hand waving, we do it rigorously. Actually, physicists are a little careless with their hand waving sometimes, and mathematicians are critical in physics. Say you're too hung up in the fine points, okay? There's justification to both, depending what you want to do. Anyhow, there it is. And what's that integral? Well, that integral is just 2, because it's going to be negative sine theta evaluated here and here. You know, that's something else important out. This is negative, okay? Because that integral will give you negative 2. I'll say it's this times negative I. It's obviously in the negative I direction, which means that I should have had a negative sign on this out here and a negative sign on this. And now the integral, the antiderivative of cosine is negative sine. Negative sine evaluated at negative pi over 2 is negative of negative 1, which is 1. Okay. Say that right. That's being subtracted from this. Might have some dumb in there, but it's negative 2. Then k lambda over r. Comes out very simple straight. Yeah, and I confused myself with signs because I didn't include the negative there. So that's right. Okay. So again, the integral is very simple. It comes from analyzing a typical increment from all the integrals that we get, almost every integral. All we have to do is look at a typical increment. Well, first we partition an interval of some parameter. So, and then we look at what happens in the typical partition. And then our integral just falls into our hands. We're going to do this again and again. Does that one make sense? 2/3 of the way? Okay, well, might need to do a little calculus review, although if you're in the multivariable calculus class, and everybody here is either in it or has had multivariable calculus. If you're in my multivariable calculus class, we're going to reinforce this again, again, and again. We get to chapter 15, okay? Yes, we're in chapter 14 right now, so it's coming up fairly soon. And we're also going to take it way beyond the stuff that we can talk about. And of course, whose prerequisite is only first year calculus, okay? But you get more insight out of that. So it's a good situation for that. Okay. We'll look at another situation, okay? Let's say I've got a ring of charge. That big around, that looks like 12 centimeters, 15 centimeter radius. Okay, whatever, the radius, it's got a radius, okay? Then we're going to put it in the XY plane with the axis through the center. We're going to figure out the field at any point of the z-axis. Okay. And we can draw that pretty easily. There's a X or Y. And I'm C. Here's the point where we want to figure out the field or the force. Then we think, okay, we'll put a test charge Q there, whatever charge we might want to put there to measure the field. And then we sketch ourselves a nice square down here in the XY plane. And then we fill it in with a circle. Up to the z-axis over here. And it goes through the X and Y axis. Okay, so there's a ring of charge. We're going to use A for the radius. I probably should use A for the radius up here. let's be real specific. I'll say the total charge is Q sub ring. Okay. Now I want to parameterize something so that I can talk about a specific increment of the ring and the effect of the charge on that increment to this point. So we've got a question, comment, or solution. I don't know. We'll see. Okay, now again, the question or the comment was we can use symmetry here. And it's going to turn out that all we got to have is the Z component of the electric field induced here, not induced, but the electric field due to this charge at this point. Okay, and it's because I'll draw a couple lines. So, okay, so we got that's a bad looking circle, but we'll do it. Okay, so there's our axis through the center. If I've got an increment on this side, and looking at this point, then my field due to the charge in this increment would be here, assuming you have positive charge. Okay, now let's back up a second. If this assumed positive charge, right? But we use this as a schematic. If the charge is negative, then lambda is going to be negative, and it's going to reverse it, and it's going to be that way, right? Okay, so if you have a negative charge in this thing, everything will be in the opposite direction, but that's taken care of by the fact that you got lambda as a multiplier, and if lambda is negative, then your vector is going to be in the opposite direction. Okay, well, you know, when I wrote this down, write my I component for this. My signs. You should ponder them too. I'm not sure everything works out as I said. Anyhow, from this increment, you could have an increment opposite. It's going to exert force along the R vector from here to here. And if the charge density, if the total charge Q is positive, then you're going to have two vectors like this. Okay, so this vector here is kind of coming out of the board at you, and this is kind of going into the board. It doesn't really look like that. But the net here we'll call this, using the notation we did before. I'm just going to call this an E. It's going to be one of our E sub i's. And I'm going to call this one E prime. It comes from the equal increment on the opposite side of the origin. And it's clear by the symmetry that only the Z component remains. So we have the two Z components. And this vector here is going to be the Z component of E plus the Z component of E prime. They're equal. The Z components are equal. Again, the XY components are equal and opposite. So you're just going to have 2 times E sub Z, which it kind of means that all you really have to do is partition half of this thing. Okay? And just double it. We're going to partition the whole thing anyway. But that would be perfectly valid to partition half of it and make a symmetry on it. Question, comments? Don't know. Okay. Yeah, and what was just said really comes down to this. whatever this increment is, it's going to give you the z component. If you just divide the entire circle by the length of the increment, whatever parameter you use for the circle, how many of these increments are there in the circle, you just multiply that number by the z component and you get the result. Okay? That's kind of a shortcut. We don't want to take that shortcut because we want to think about how we set up these integers. But symmetry arguments are that powerful, you can do that kind of thing. Because the angle of your R vector, the R vector going from increment to field point, is always going to be the same. The angle of that vector with the z-axis is always going to be what? The arctangent of radius of the circle divided by z. Okay? And you can use that to write down the expression almost instantly. Still, symmetry arguments are great and they're that powerful. Okay? We cut out a lot of stuff if we have the right kind of symmetry, but we don't always. Although often in electromagnetism, we can't do much unless we have some symmetry, so we do take those shortcuts a whole lot of times. Okay, well, back to this. Let's just partition this. What parameter are we going to use to parameterize this circle? Okay, well, we got to partition some interval. We got to use some parameter. Now, there are two pretty obvious parameters that we could use here. One is the same parameter we used here, which would be theta. Now, you're going to do a whole circle. We're going to do the whole circle. We're not going to actually use the symmetry argument, although we certainly can. And we're going to see from the expressions we get how the symmetry argument works out. Okay, in any case, it's interesting to see how that plays into the integral. And it's worth seeing, it's worth knowing. Okay, so again, we could partition the angle. The angle would go, if we're doing the whole thing, and we can go from, negative pi over 2 to 3 pi over 2 if we wanted to. That would get the whole circle. Okay? But generally, we're just going to go from 0 to 2 pi. That's an actual angular increment that we would use. And we set up our delta S is just the same as we did over here. I'm going to do it in terms of arc distance, so we just have a delta S directly. Okay? So parameterize it by theta from 0 to 2 pi. And we're going to do this one since we did a theta last time. The arc distance goes from 0 to 2 pi a because that's the circumference. We want to get the whole circumference. We don't want to get any more than that. Okay, we just get the whole circumference though. Okay, then, so there's our partition. Now, at this point, further than that, we'll use that much. Okay, so It tells us immediately our integral is going to be with respect to s, and the limits are going to be from 0 to 2 pi a. Okay, typical increment be our ith increment with sample point si star running from si minus 1 to si. Okay, well, what I then know about the typical increment, let this be the typical increment. What's the arc distance? If s is the distance I've gone along the arc, well, that is the arc distance, what I just asked was. Because what are the coordinates of our point? Sample point. Well, what we have to do is we have to say that we got some angle here. Theta sub I. We can't really escape the fact that we've got an angle. So on this increment, A cosine theta, A sine theta. And we'll say theta I star. Theta I star is 2 pi times S I star divided by 2 pi A, which is Si star over A, which we could have said just by the definition of a radian. We know the arc distance from here to here. Okay. And we know the radius of the circle. So the radius times the angle is the arc distance. So the angle is the arc distance divided by the radius. All right. Now there are different ways to get the components of our R vector. Our R vector goes from here to here. And that will be our R sub I vector. vector. Again, I'm just debating the coordinate system I really want to use here. You've got a triangle here. Okay, you've got a triangle with an A here and R sub I here and your Z coordinate here. So if I want to draw this triangle, I've got my Z, which is just a Z coordinate of this point. I've got my R sub I vector, and I've got the radius of the circle here. So I can say that this angle is the arctangent of A over Z. Yeah, and I'm debating about how much detail I want to put into this thing because we cut a lot of it out. We cut all of it out with symmetry argument. But I don't want to cut all of it out. So I should do the magnitude of this, square root of Z squared plus A squared. Making angle arctangent of Z over A. With the Z axis. Now, I'm going to use a simple picture. Again, here we've got it. Here's our R sub I vector. Length. Z squared plus A squared, because this side is Z and this side is A. And we got this angle here. And it's going to give us a vector up here. Of delta EI. That vector, but here's the Z component. So what is the Z component of this vector? Okay, I said you got similar triangles. This triangle is similar to this triangle, right? It's what are your corresponding sides? This delta EI Z, the Z component of delta EI, is in the same proportion to your EI vector, like your EI vector, as this side is to the length of the RI vector, right? We can say then that delta EI Z, magnitude of the contribution in the Z direction, is delta EI multiplied by Z over the square root of Z squared plus A squared. That makes sense? I mean, this is shorter than this by the same proportion that this is shorter than this. It's just standard similar triangles. We go to angles. I told you the angle here is arctangent of A over Z. And we could say that, okay, it's going to be this length, the length of delta EI, times the cosine of the arctangent of A over Z, because here's your arctangent of A over Z, and this will be the cosine because it's adjacent and all that stuff, okay? But the cosine of the arctangent of A over Z, you just draw a triangle with opposite side A and adjacent side Z, and figure out that R is a square root of A squared plus Z squared. So the cosine is going to be Z over Z squared plus A squared. So that's just the cosine of that angle. Now, if you did that in pre-calculus, cosine of the arctangent of whatever and that stuff, by constructing triangles, it should refresh you. But otherwise, just kind of take it as a lesson. It's a handy thing to be able to do because you run into it a lot. Okay. So anyhow, okay, you get this. And EI, delta EI is what? It's lambda delta S over Ri squared too much stuff. Delta EI is K times the charge you have within the increment, which is lambda delta S, over Ri squared, Ri being the length of this vector. And you simply write that Ri squared is Z squared plus A squared, because right there is Ri, and there's two legs of the triangle. Z component of delta EI is this times Z over that square root. There it is. And of course that comes out. I'll write it this way, K lambda delta S, the S on it, times Z over the cube of Z squared plus A squared. Now, there's nothing in here that varies with your position on the curve, okay? Every one of these quantities is constant. Z is what it is. You try to find the field at point Z, okay? Or the, you know, 0, 0, z. So z is whatever order you're trying to, you know, it's the position on the z-axis in which you're trying to calculate the field. Okay. A is the radius of the circle, so it doesn't vary. Delta S, we're assuming equal increments. I'm not sure I said equal increments, but we kind of make that assumption. Okay. Lambda is your density and K is your electrostatic constant. Okay. 9 times 10 to the 9th Newton meter squared Coulomb squared. Thus, the sum of your EIZs and they should have written a square root to the cube. It's z squared plus a squared to the 3 halves. No. Yeah. Times the sum from I equals 1 to n of your delta S. And what's the sum from I equals 1 to n of your delta S? So tell me. What's S1 minus S naught plus S2 minus S1? Yeah. Was I not recording before? Yeah, okay, hang on. Okay. Okay, so we saw this. You know, that's what this and this was. You said, well, it's just S2 minus S naught because you have a minus S1 and a plus S1, right? Now, if I add this one to S2 minus S naught, well, I've got a minus S2, so I'm just going to be left with an S3 minus S naught, right? Now, there are no plus S naughts on this, so S naught is going to still be there. But everything subtracts out except Sn. So convince yourself of that because it's an important idea. Sn minus S naught is 2 pi a minus 0, which is 2 pi a. Okay. Also, I mean, if you look at the partition, if I add up all these increments, each one has length delta S, which is 1 over n times 2 pi a, and there are n of them. They all add up to 2 pi a. We're just breaking this thing up into increments, even if they aren't all equal. Okay. The sum of the lengths of the increments around the circle is just the radius of the circumference of the circle. Make sense? I gotta think about it until it does. Think about it until it's obvious. Okay, so the sum of our delta S's, don't really have room to write it, but that won't stop me. A lambda z over the square root, well, over the quantity, z squared plus a squared times 2 pi a. If we use equal increments. If not, we do a limiting argument and we still find that our delta S's add up to 2 pi a. We don't even need a limiting argument to do that. Okay. So the symmetry of this situation shows itself in a number of ways. We can always just calculate the z component of the electric field. Then all we have to do is count how many of them. Okay. And multiply how many by how wide they are. And we get 2 pi. There it is. Okay, that's kind of a couple of interesting arguments that get to the stuff that in the problem set that I judge to be the thing that's most likely to cause you to stumble. Okay. Now, in the problem sets, you know, the first 10, 12 problems, first half of the problem set is conceptual stuff. Okay. If you chase positive or negative charges away from this end of a rod, what happens to the charge in this end? Or what does the charge in this end do to a positive charge? Well, it's going to attract it because the repellent is going to be positive. But questions like that, because you want to get used to the idea of how charges behave. Then it gets into Coulomb's law. And then you get into the kind of stuff that we wrote out last time and the stuff we're talking about this time. Does that make sense? You got till I get to next Monday. There'll be a chapter a week. Okay. And the next chapter is, I think it's a chapter on electric fields. I haven't looked that far ahead, but and when we do the chapter on electric fields, you end up with a lot of symmetric type distributions. Like you end up with an infinitely long cylinder with charge evenly distributed, and ask what happens. Okay. Or an infinite flat plane, or an infinite line charge. We talked about that last time. We developed the integral last time. I got to do the integration and do the integration. Don't let Wolfram do the integration for you. These are standard calculus 2 integration techniques. Okay. And you want to be aware of them because they can be informative. They can inform you about symmetries. They can inform you about relationships in a way that letting Wolfram do it doesn't. Okay. Actually do the calculus. Okay. That isn't that bad in this course.